Next, we need to discuss what happens in games when there is no strict dominant strategy equilibrium. What happens if players do not have strategies that are always the best strategies for them, no matter what the other players are doing? Central to an extension of the idea that players play what is optimal to them is the idea of the best response. If players do not have strategies that are always the best, it means no matter what the other players are doing, at least they have strategies that are sometimes the best of what they could do. Sometimes means it depends on what the other players are doing. In almost all interesting situations, it's actually the case that the optimal thing a player can do depends on what the other players are doing, which is obvious in board games. So how do we formalize this idea that players try to play what is optimal for them given what the other players do? We introduce the concept and the notion of a best response. A best response of a player is a strategy of that player, which is a strategy that maximizes this player's payoff given a specific strategy profile S minus I of what all the other players are doing. So strategy, more formally, strategy Si of player I is a best response to his opponent's strategies S minus I. So best response is only defined with respect to a given opponent's strategy profile S minus I. So strategy Si is a best response if the utility, if the payoff, if Fi is played, is at least as large as a payoff that player I could get if he played some other strategy Si prime. Okay, so if the other players play the strategies S minus I, Si is the best response if it gives the highest payoff of all the available strategies to this player. A rational player who therefore believes that the other players are playing the strategies S minus I, the strategy profile S minus I, would rationally choose by playing a best response to that. Obviously, a strictly dominated strategy is never a best response, because if a strategy is strictly dominated, we know that there is another strategy of that player that is always better, no matter what the other players are doing, and therefore the original strategy can never be a best response. And it's also true that a player can have more than one best response under certain circumstances. The reason for that is that for best response we just require that the payoff is weakly larger than the payoff of some other strategy or of all the other strategies. So sometimes it could be that they are equal, and therefore it could be that this condition here is true for more than one strategy of a player. What do we do with this concept of the best response? It should be clear to us now that if a player is rational and wants to maximize his payoff, he or she will play a best response. The big problem for the player is a best response to what? A best response is defined with respect to what the other players are doing, but how do we know as a player what the others are doing? And now comes, if you want, the genius idea of John Nash, who made the following assumption or the following statement. He said it seems rational that if a player understands that also all the other players are rational and also play best responses because the best response is the best they can do, then I might be able as a player to predict what the other players are doing, because I know they play a best response to what they think I am doing and the other players are doing. And therefore, in a so-called Nash equilibrium, the assumption of the other players playing a best response might be enough to tell me what they are actually doing. Because to have a stable situation, a situation where everyone plays a best response, we need to have that every player selects a strategy or one of the strategies that is optimal given that what the other players are doing, which again is optimal with respect to what the original player was doing and all the other players are doing. So the situation of mutually playing best responses is what Nash thought is the outcome of a game. And his justification was that is what a rational player would do. He can anticipate what the other players are doing by anticipating that they will also play best responses. Also, the other players don't know with respect to what they should play best responses, but they make the same reasoning as all the other players. And as they all know that they're making this kind of reasoning, in the end, they all play best responses with respect to each other. And this enables us to calculate what these strategies are. More formally, a so-called Nash equilibrium is again a profile of strategies. We already know that similar to the equilibrium we had before, the strict dominant strategy equilibrium. So a profile of pure strategies, which now is denoted by S star, the stars for Nash equilibrium. If every single component of this profile, that means S1 star to Si star, is a best response to the strategies S minus I of all the other players that are also part of the Nash equilibrium. Or in other words, every component of the Nash equilibrium is a best response with respect to the strategy profile defined by taking all the strategies of the other players from this Nash equilibrium. This has to be true for every single player. So, if you take player I, it must be true that for him, the utility, if he plays Si, actually there should be a star here, Si star, and the other players stick to what they should play in the Nash equilibrium, then player I knows he will get at least as much as if he played some other strategy as I prime. And this must be true for any strategy. And for any, this must be true for any player. So we have some kind of a recursive definition here in the sense that what is best for player I depends on what the other player is doing, and what's best for them depends on what player I is doing. And in equilibrium, they mutually anticipate correctly what the others are doing because they know they will also play equilibrium strategies, and therefore it all comes together. Again, some remarks. First, as before, a Nash equilibrium is defined as a strategy profile. So it's not defined by the outcomes, that means the payoffs that players get, it's defined by what they are doing, what their strategies are that they select in the respective equilibrium. So for example, if I asked you to write down a Nash equilibrium in exercise or an exam, don't write down the payoffs of the players in the Nash equilibrium, write down the strategies that they will select. For an example, please refer to my separate video on the prisoner's dilemma. Obviously, strict dominant strategy equilibrium, the one we already know from a previous video, that is also a Nash equilibrium because there they play best responses to any strategy of the other player, so in particular also to the strategy that is part of the equilibrium, and therefore it's also a Nash equilibrium. It could be for some games, and I will give you an example in the lecture, there might not exist such a Nash equilibrium in the way we define it here. We will then say it does not exist in pure strategies. So far we've called all the strategies that we looked at pure strategies. And this will require us to introduce or to extend the notion of a strategy a little bit to make sure that any game in the end does have a Nash equilibrium. But before we do that, I would like to go through a simple example and show you how you can find a Nash equilibrium in a simple matrix normal form game. I will do this one example, and for further examples I would like to refer to my lecture. Again, there's also a video on another example called the prisoner's dilemma, but let's start with this here. What you can see here are two players, player 1, player 2, so two players play a game. Each of the two players has three strategies. So player 1 has the strategy U, the strategy M, and the strategy D, and player 2 has three strategies L, C, and R, left, center, and right. And what you can say in the matrix are the payoffs of the players. So the first number is always a payoff of player 1, and the second number is a payoff of player 2. So for example, if player 1 plays M, so player 1 plays M, plays here, And if player 2 plays R, plays here, player 1 will get 3 and player 2 will get 6 as a payoff. So now let's have a look at what these players could do. Let's look first at player 1 and try to figure out what player 1's best responses are, because we know if we want to find a Nash equilibrium, we need to find the player's best responses. Let's first consider a situation where player 1 thinks that player 2 plays L. Okay, so if player 2 played L, player 1 would choose as a strategy either M, because M gives 4, or D, because D also gives 4. These are the two best responses to the strategy L of player 2. U is not a best response because U would only give 3 if player 2 played L. So there are two best responses of player 1 with respect to the strategy L of player 2. And these strategies are M and D. And therefore these could be part of a Nash equilibrium. Let's continue and check what happens if player 2 plays C. We don't know yet, and player 1 also doesn't know what player 2 actually does, so we have to go through all the possibilities. If player 2 played C, we see that only D is a best response for player 1, because D gives 9, which is more than 8, and which is also more than 5. If player 2 played R, player 1 would optimally choose either D or U, because they both give 6, and that is the highest number in this column. That means the highest payoff player 1 could get. So we now know all the best responses of player 1, depending on what player 2 does, whether player 2 plays L, C or R. So now we have to look at the best responses of player 2. Because we know Nash equilibrium, they play mutually best responses with respect to each other. So let's assume let's look at what player 2 does if player 2 thinks that player 1 plays U. Again, we don't know, or player 2 doesn't know what player 1 will actually do in this game, so we have to go through all the possibilities. If player 1 played U, then player 2, and now we have to look at the second number in this row, because player 2 can either select L, C or R, so he could either get 3, 1 or 2 as a payoff. And because 3 is the largest, we can see that L is the best response with respect to U. And the same now we do for M. If player 1 is assumed to play the strategy M, player 2 optimally would select R, because R then gives 6, which is more than 4, which is what he would get if he played C, and which is also more than 1. If player 1, and now we've done almost all the cases, if player 1 plays or played D, then for player 2 it would be optimal to play R, because this gives 8, which is more than 6 and which is also more than 0. So now, because in a Nash equilibrium we have mutually best responses, only those cells, if you want, in this game can denote a Nash equilibrium if we have underpinned both numbers. That means if player 1 and player 2 play best response. As you can easily see, this happens here. So player's 2 strategy R is the best response with respect to D, and D is the best response with respect to R. For example, this up here, UL, is not a Nash equilibrium. Why is that? It is true that player 2 plays the best response. Here, L is the best response with respect to U. We already have figured that out. But player 1 does not play a best response to what player 2 does, because U is not a best response with respect to L, because M and D are the best responses. So this here is the only Nash equilibrium in this game.